So we're definitely talking about derivatives. Like we're fully in derivative land. Let's talk about derivatives and differentiability. So just a couple of things I've observed that you might want to be thinking about. If you've got a function, it's a straight line, you know the derivative, because when we're thinking about the derivatives, we're thinking about rates of change. But the most common way we think about that is as the slope of the tangent. So if you think about this line, f of x equal to 4x minus 3, it's a line, and any tangent line is the same line. Like, it's kind of weird to think about. If you draw this line, which is vaguely like this, I don't want to try drawing the tangent line because the tangent line at any point is the line itself. And the slope of this line is 4 everywhere. So we would very easily say that this line has a derivative that is 4, no matter what x is. And that's just something, instead of remembering, like there's a rule to take the derivative of this, we're going to learn it soon. But really what I want you to do is like, oh yeah, that's a straight line. It's got a slope of 4 everywhere. It's derivatives 4 everywhere. And in a similar way, if you have a line that's a constant function, like g of x equal to 6, well, that's a horizontal line. And it looks something like this. What's the slope of that line? Yeah, it's 0. And that line has infinite run and 0 rise. And rise over run would be 0. So the derivative here is 0 because this line has a slope of 0. So just a couple of key facts. There's one other thing I want to say here. Oh, yeah. So there, sorry, I got stuff all over the place. A couple other interesting things. This function, the absolute value of x, looks like that. Welcome. Thanks. This function is not differentiable. Well, so again, some language stuff, right? If someone said, James, is the absolute value function not different or differentiable? I would say no. But what I would really mean is it's not differentiable everywhere. Right? This function is differentiable at almost every point, except for one. That's enough to say it's not differentiable. But really, we should be more specific. We say it's not differentiable at x equals to 0. This pen is dead. Thank you. Thank you. What we have at 0, 0, we have a corner or a sharp turn, or I like to call them pointy points. When you have a pointy point, it's not differentiable. And what I'm kind of thinking about is the slope over here is -1. The slope over here is +1, and we don't have a smooth transition from the slope being -1 to +1. In fact, if you were going to graph the derivative of this, well, I know that all the way over here, the derivative is -1. The slope is always -1 over here. So to the left of 0, the derivative is -1. And to the right of 0, the derivative is +1. Well, it's not the best. And then at 0, the derivative is completely undefined. There are ways of showing this using the limit definitions. It's not super, like, I don't feel like that's something we do so much in this class, but we could totally, like, if you want to show that this function is not differentiable at 0, well, how do we find the derivative at 0? Well, let's go back to the limit definition. It's the limit as h approaches 0 of f of x plus h minus f of x all over h. And we're specifically using the absolute value function. So it's going to be the limit as h goes to 0, the absolute value of x plus h minus the absolute value of x all over h. Oh, but I'm being a little too general here. I don't want to find the derivative everywhere. I specifically want to find the derivative at 0. So what I'm going to do is I'm going to say, well, that's f prime of x. F prime of 0 is going to be the limit as h goes to 0 of the absolute value of 0 plus h minus the absolute value of 0 all over h. A little better, because now the absolute value of 0 plus h is just the absolute value of h. And what's the absolute value of 0? I know it's not very exciting, it's just 0. Then you may be like, well, how do we deal with this? Well, for a limit to exist, both sides have to have the same value. So we're going to look at the limit from the left and the limit from the right. We do the limit as h approaches 0 from the right, h is positive, and the absolute value of a positive number is just that number. So we view the limit as h approaches 0 from the right of just h over h, because h is already positive. H divided by h is 1, and the limit of a constant is just the constant. Which makes total sense, right? If you're looking at this at 0 and you're approaching it from the right side, the slope is definitely positive 1. The limit is positive 1. On the other side, if we do the limit as h approaches 0 from the left, well, now h is negative. And the absolute value of h is, and this is always feels like it's a little bit of a struggle, the absolute value of h is negative h. Cool? I can talk more about that. I can talk more about it. So the reason it's negative h is because h is a negative number, but I want the absolute value to give me a positive number. So if h was like -3, the absolute value of -3 is -3, which is +3. So I'm taking that negative number, right? H is negative, and turning it into a positive number by multiplying by -1. And then those cancel, we get the limit as h goes to 0 from the left of -1, which is -1. And since the two limits aren't the same value, the overall limit doesn't exist. But in this case, the limit not existing means the derivative doesn't exist because the derivative is the limit. So here we're saying, oh yeah, this function f of x doesn't have a derivative at 0. Wow, words. Or written more nicely, f of x equal to f of absolute value of x is not differentiable at x equal to 0 because the derivative, which is a limit, doesn't exist there. But graphically, it's very easy to see this if you see a pointy point or a corner, or the other type of pointy point, which is called a cusp, like this function, f of x equal to x to the 2/3. I call this the bird function. You'll see why in a moment. I'm going to plot a few points, 0, 0, 1, 1, and 8, 4. I don't really want to plot 8, 4, but sure, it's there. And then it's the same to the left, meaning it's reflected. This function is an even function. It has symmetry about the y-axis. If you plug in -1, you get +1 out. If you plug in -8, you get +4 out because you're squaring and cube rooting. So this looks like this. Like that. And I call it the bird function because it kind of looks like birds a young person or a poor adult drawer might draw. Like that, right? Birds. Kind of looks like a bird function. You don't have to agree, it's all right. But the point is, it's pointy. That's definitely a pointy point. That's a cusp. And although my drawing is not excellent, what's happening here is that the slopes of the tangent lines here are getting very, very large. Right? Those tangent lines are getting closer and closer to being vertical tangent lines. And the vertical tangent line has an infinite slope. So here, this function, that pen looks gross. Okay. Good thing I got a lot of them. This one, wow, What's going on with my pens here? Like exploding or something. That's weird. Got like, it's kind of, not your problem. All right, so, yeah, what's happening here is that this function is not differentiable at x equal to 0 because we have a vertical tangent line. We have a cusp. Or as I'm going to say, if it's pointy, it's not differentiable. If you had to make a hard turn, a sharp turn, it's not differentiable. So if you think about like, welcome, you can think about like a car driving on this road, like from the top down, it's making a real sharp turn to go around that corner there. Right? That's not differentiable. We want nice, smooth driving like this, not like that. Okay, so not really. I don't think it's super duper important, but you could also show, I'm not going to do it, but I can point out that you could show that this function is not differentiable at x equal to 0 by trying to compute the limit as h goes to 0 of f of 0. Oh, we're almost there. I've written most of it out. I guess we'll do it. And we really are almost there. So what's f of 0 plus h? Well, it's h to the 2/3. And f of 0 is 0 to the 2/3, which is 0. Again, h on the bottom. And when we simplify here, h to the 2/3 over h is just h to the negative 1/3, or as I would prefer to write, 1 over h to the 1/3. And as h goes to 0, what's this limit? I mean, it's some sort of infinity on either side, but right, it's infinity from one side and negative infinity from the other side. So this limit doesn't exist. Even if it was infinity, it's still not a real number, not existing. This slope of the tangent line here is infinitely large. So yeah. So there's something I should say. No, that's right. Yeah. So when I think about differentiability, I generally think of a function being smooth. There's no jagged edges, there's no sharp turns, there's no corners, there's no cusps. And most of the time that's enough. The one exception to that rule you should keep in mind, not the only, but the primary example of exception is this function. The cube root of x. That function is smooth. Looks kind of like that. Definitely smooth. But it's not differentiable at 0 for the same sort of reason the previous function wasn't. If you try and do the limit definition of prime of 0, it's going to be the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. Look what's going to happen. The limit as h goes to 0 of the cube root of h over h, which is going to be the limit as h goes to 0 of 1 over h to the 2/3 power, which is infinity, but infinity is not a real number. This limit doesn't exist, right? If someone says the limit's infinity, that also means the limit doesn't exist because it's not an actual number. This tangent line here at 0 is a vertical tangent line. And if the derivative is the slope of the tangent line, and the vertical line has an undefined slope, that means the derivative is undefined here. So if you have a derivative with a vertical tangent line, that means the derivative there is undefined because the slope is undefined. So just a few kind of ways you can think about differentiability. Most of the time, if a function is smooth, it's differentiable everywhere, except if you have a vertical tangent line there. That doesn't happen much, but it does happen on here. Anything else I want to say there? I don't think so. Right. Cool. let's get some graphs. These red pens are, I don't know about these red pens. Still plenty of ink. I guess I could try writing with it. We'll see how it goes. So sometimes we want to be able to sketch the graph of a derivative from the graph of a function. Let's say our function looks something like this. We would like to sketch the graph of the derivative. So if I'm doing it personally, I want to kind of draw my coordinate system directly below it so I can kind of like make things match up. So let's do that. Maybe like I think it just, it's weird. Sorry, I keep looking at my pens like they're important, but they're not. So what I want to specifically identify are the peaks and valleys. Because those are going to correspond to where the derivative is equal to 0, because that's where our tangent line is horizontal. Yeah. So for graphing the derivative, those points there are going to be places where the derivative is 0. And that's where I would always start. If I'm trying to graph the derivative from a function, take your relative maxima and minima or your peaks and valleys and say, oh, that's going to be where the derivative is 0. And then if the function is getting smaller, well, again, if you don't even have to think about slope here. You just think about rates of change. If the function is getting smaller, it's changing in a negative way. It's decreasing. So our derivative should be negative. So it's going to look something like, I don't know, something like that. And again, your graph is not going to be perfect, right? It's just going to be like, I know it's negative. It's steeper here, right? The slope of the tangent line is more negative there than it is over here. So it's more negative values over here, less negative values over there. And then from here to here, it's going to be somewhat positive. And it looks like about right there is probably where it's it's the steepest slope it could be in that little region, right? So right about there is probably where it's going to top out for the derivative. So something like that. Right, that's the point where the derivative is the biggest, or the slope is the steepest in that little region. And then we get back to this point here, we are back to the derivative being 0, and now we're going to go negative. And again, from here to here, I'm going to go from the derivative being 0, a little bit negative, more negative, and then it's going to be less negative. Steeper slope means more, shallower slope means less. And it doesn't matter negative or positive, right? If there's a steeper slope, the steeper slope going that way, right? Super positive. The steep slope going that way, super negative. So here we have slightly negative, and then more negative, and then bottom out, and then less negative. And that point there probably corresponds to like that point right there. And finally, after this point, it gets more and more and more positive. Or I should say the slope gets steeper and steeper and steeper. So the derivative gets more and more positive. And that would be a perfectly fine depiction of what the derivative looks like from the original function. It's not a really good example. Don't hesitate to ask questions if you got it, but let's do a few more. Oh, can you guys hear me in Zoom? Because I'm looking at the mic and it's not on.
Yeah, I can hear.
Oh, good. That's good. I'm sure it's using the computer's microphone, but yeah. It's like, oh no, they didn't say anything and the mic's on. I'm glad you guys can hear me. Great. Okay, so let's look at another example. Actually, let's look at this example I have in mind. So there's two very special functions. I think they're worth knowing because you're going to see them in the middle of it anyway. I'm trying to grab pens. I know don't work. Green. Look at the sine function. Which has a period of 2 pi. And we typically graph it by breaking it into 4 equal sections. Has a maximum value of 1, a minimum value of -1. Usually starting at 0 and then going up to 1 at pi over 2. Back to 0 at pi. down to -1 at 3 pi over 2, back to 0 at 2 pi. And then it repeats, right? It's periodic. It does the same thing over and over and over again forever and ever. What I want to point out is you can use this graph to graph its derivative. All right, so let's look at the peaks and valleys first. So at pi over 2, we just got a peak. So the derivative is going to be 0. And also at 3 pi over 2. We have a place where we have a horizontal tangent line with the derivative of 0. So we got those zeros there. And then over here between 0 and pi over 2, we got a positive slope. So starting out positive and then it's getting closer and closer to 0. And that will tell you the slope there looks like it's about 1. Like if you draw the tangent line there, the tangent line looks like it's probably the line y equals x. It is. It's not just close to it, it actually is that value. So we know that the tangent there is a value of 1. And the tangent over here has a value of -1 at pi. And then at 2 pi, we should be back to where we were at 0. So it should have the same value. And here's what this looks like. Anybody want to venture a guess as to what function this might be? It is definitely cosine of x. So here's some good visual proof that the derivative of sine of x is cosine of x. We're going to learn this a little bit later, but it is true. The derivative of sine of x is cosine of x. And you could do the same thing. We're not going to, but I encourage you all to take the cosine graph, try and draw its derivative, and you'll see that its derivative is negative sine. It looks like the sine function, but flipped over. It's a good exercise. I encourage you all to do it. Yeah, derivative sine is definitely cosine. Let's look at a few more examples. It is a useful skill to be able to take a function and draw its derivative just based on the graph. Let's take a look at this one. Function looks kind of like this. We've got horizontal asymptotes. So I want to draw the derivative of this. It's not a vertical asymptote, it just goes down that way. So again, I'm going to line up my axes to make it easier. It looks like maybe, this is kind of a maybe, but it looks like it kind of flattens out right there for just a second. It does. I mean, at least I tried to draw it so it did. It looks like there's a tangent line there. Now, you might be looking at some of these tangent lines I'm drawing, but James, your tangent line is going through the graph. That happens sometimes. Specifically, it happens at what's called an inflection point. The example I would encourage you all to keep in your minds of a graph where the tangent line goes through the function is the cubic function. So y equals x cubed, which I'm never good at drawing. The x-axis is a tangent line to the graph at the origin. So if you draw this graph, it looks kind of, oh my God, yeah, good job. It's kind of like that. I mean, but not. You guys hopefully all know what the cubic function is. How about we use the tools we have available to us? How about that? So let me just show you. So there's the cubic function. And you can see that if you draw, I mean, it's there, but we can also put it in y equals 0. That line is tangent to the graph. It touches it at one point. It happens to be a tangent line that goes through the function. And those tangent lines are special. They occur at what are called inflection points. So yeah, kind of a neat little tangent right there, but you can't have a tangent that goes through the function. I kind of think of it as where the function kind of flattens out for just a second, but still continues doing the same sort of increasing or decreasing behavior. All right, so that's what that looks like there. We try and graph this thing. Let's see. So it's definitely in. So it looks like it's increasing the whole time, right? Like from left to right, it's getting bigger and bigger and bigger and bigger and bigger. Stops for a moment and then gets bigger and bigger and bigger and bigger and bigger. So if I was going to try graphing this, I would say, okay, well, here my derivative is going to be 0. But other than that one point there, I know my derivative is always going to be positive. So it's super positive over here and then becomes less positive. So probably going to be something like this. And then after here, it's not very positive first. And then, oh, and then it looks like it kind of has a most positive spot, like maybe right about there. Right there is where it looks. Now I should say, this other point I'm trying to identify, I know we haven't talked about inflection points yet, but this is also an example of inflection point where the direction of the derivative kind of changes. The derivative is very, very positive, and then, right, or I should say, the derivative is increasing, and then it starts decreasing. And the slopes of the tangent lines are getting more and more steep, and then less and less steep. But really, you should just say, I'm looking for this point where the steepest slope is occurring. And that's, I'm going to draw it terribly. It should go through the, wow, yeah, lovely, right? So good. Sometimes my drawing skills, as you guys might have noticed, are lacking. It's not for lack of practice. It's just some people are better drawers. So there is our point where the derivative is as big as possible, and then it's going to get smaller, and my tangent lines are going to have less steep slopes. And it looks like we're kind of flattening out. Like it's not exactly horizontal over here, but it's very, very shallow tangent line slope. So I would guess it probably has something like a horizontal asymptote, like that. Because the slope is approaching 0 as x is approaching infinity. I think I had one more example I really want to make sure. No, yeah. Sure, let's do one more and then we'll move on to, I think we should start talking about the power rule. So, yeah. Let's look at this funky looking graph. Okay, this looks terrible. That's my function. And I want to draw the derivative of this function. Let me ask you all a question. How many places do you see where the derivative doesn't exist? Okay, I was like, I think 2, but you guys are right. I think actually you're right. 3. Right? There's definitely one there. There's a pointy point there, or corner. So the difference between the corner and cusp, not that it really matters, but the corner is like where you just have straight lines whose edges meet, whereas the cusp is where you have this like where the slopes get infinitely large or negatively large kind of deal. So I have a corner there, I have a corner there, and then I have a cusp right here. So yeah, it looks like 3 places where the derivative is not going to exist. Let's try and draw the derivative. So the slope here is some negative number. It's constant though, right? The slope is always the same thing in this little region. So whatever it is, I'm going to say it's like -2. It's not going to exist right there. And the slope to the right is probably +2-ish, maybe slightly. It looks maybe slightly less steep than that one. Again, we're not going for total accuracy here, right? We're just trying to be like, I have a good idea of what the function looks or the derivative looks like. So positive, and then it's going to go from there to there. And then from here to maybe like here-ish, it looks pretty flat. The derivative is looking like 0. And it is open there because again, right, we can't say that it's, if it's not 0 from both sides, we can't say it's 0 there. Right, the left, so if the left and the right derivative aren't meeting up to come to the same value, we can't say it's anything at that particular point. Let me say that again. If I ask you about the derivative of this function at this particular point here, I would say the limit of the derivative from the left is positive whatever, and the limit from the right is 0. And if the limits aren't the same, the function is not differentiable at that point. Which is why I'm going to get a little open circle here. But then here to the right, there's no jarring corner here. So it's going to go from 0 and then it's going to start getting larger and larger and larger and larger and larger. How large? Really large, because the slopes of the tangent lines, the tangent lines are becoming closer and closer to being a vertical tangent. So we're going to go very quickly up to infinity. On the other side of that vertical asymptote, whoops, are my tangent lines also vertical? Yes. Are they having a positive slope or a negative slope? Very negative, right? Because we're on the other side now where the tangent lines are tangent to that. So we're going to have a very negative, which means I'm not here, we're way down here. We have that kind of vertical asymptote, right? The left-hand side, the slopes are getting very, very large positively, and the right-hand side, the slopes are getting very, very large negatively. And then we calm down a bit, we get not super negative. And then we kind of like, I don't know, we get right, very negative. Okay, maybe this is the least negative we are. About there. And then we turn back around and start getting more negative. It's not an exact science, right? The intention is not to be super extra precise about this. It's to have a good idea of how to take a function and draw its derivative. All right. Well, there's a problem one of the homelessness of it. I also thought looked worthwhile. So let's do that, and then we'll talk about the power rule for a little bit. Because we should be moving into talking about like the rules of derivatives. That's where we're going to be getting to very shortly, if you're not already there. But let me go ahead and oh yeah, this question here. So this question is, we're given there's a function f of x is continuous and differentiable, and we're given the following: the limit as x approaches 4 of f of x minus 7 over x minus 4 is equal to 19. And we're being asked, well, here it's also phrased kind of weirdly. Here's what they write: it follows that, seems not very intuitive, it follows that y equals blank is the equation of the tangent line. At y of, 2, y equals f of x at the point blank. Which just seems like not the best reason, but okay. So the idea here is, this is supposed to tell us something about a derivative in a function. And the thing that we're being asked to observe here that I don't think is super clear is that this is a limit definition of a derivative. It's kind of the alternate version of it. So we are probably mostly used to seeing that the derivative is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. That's the usual nice way of writing it. But there is another way of writing it. It's that the derivative, and it's usually written this way, it's the derivative is the limit as x approaches a of f of x minus f of a over x minus a. That is an alternatively good way of writing it. And people, I guess really people actually say that that's f prime of a, not f prime of x. Yeah. So that's the derivative at the point A, which if we look at this, we can kind of map these things to those things to figure out what's what. So looking at this here, I can see, well, I'm just going to rewrite this. This is my limit as x approaches a of f of x minus f of a over x minus a. So I think we can figure out what a is. What does a kind of have to be? It's got to be 4, right? I mean, it's as x is approaching 4 and it's x minus 4 in the bottom and it's x minus, right? So it looks like a is 4. It looks like f of a has to be, got to be 7. And then the derivative is what this limit is equal to. That's got to be 19. Okay, but now we want to answer the questions. So it follows that y equal to something is the equation of the tangent line to y equals f of x at, well, we found the point. Right? The point is definitely the point 4, 7. Right? It's the x value, which we're calling a, and the y value, which we're calling f of a. And then they're asking us to find, or they're saying it follows that y equals is the equation of the tangent line. Okay, so they're asking us to find the equation of the tangent line. Well, great. We have all the pieces we need to find the equation of the line. All you need to find the equation of the line is a point. We got one. It's 4, 7, and a slope. We also got one. It's the derivative at the point, which is 19. So then I would do it as the point slope. Yeah, point slope. The point slope equation, y minus the y coordinate equals the slope times x minus the x coordinate. And then I would solve for y, because right, they're asking you to write y equals something. Now, pro tip, don't do more work than you have to. Here's the answer you could totally type into web work and be 100% correct, if this is your problem. Right, you don't have to multiply out the 19 and add the 7 to 19 times -4. You can just leave it like this, and it's perfectly fine. Yeah, I saw that problem. I thought it looked a little weird. So that's how you would approach a problem like this. Okay. So yeah, we should do that. Let's talk about the power rule. Now, I should point out, we've kind of already started to talk about the power rule. I know we haven't used those words, but we definitely talked about the limit definition of the derivative last class on Friday. And we did some kind of funky problems where we had to, cancel stuff out and make happen. Well, let's look at a couple examples. It's going to feel a little derivative. And you can't see my smiling face, but I'm smiling a lot because it was a great pun. I mean, it wasn't a great pun, but it was a terrible pun, which is the best kind of pun. So let's find for f of x equal to x squared. We know the derivative already, but let's see the work. The limit as h goes to 0 of f of x plus h times f of x over h, which is the limit as h goes to 0 of x plus h squared minus x squared over h. And this simplifies. We get x squared plus 2xh plus h squared all minus x squared over h. And then we can cancel some stuff. X squared and minus x squared cancel. And here's what we're going to see happen all the time with this process. The remaining terms all have an h. We're going to cancel an h or factor out an h, whichever way you want to do it. I kind of like the factoring out. I'm left with the 2x plus h, and then those cancel. So you end up with 2x plus 0, which is 2x. So no big surprise. The derivative of x squared is 2x, just as I'm sure many of you already knew. But we can keep doing this. So we could totally do this for f of x equal to x cubed. It gets a little bit hairier with the algebra, but not terribly. And this is where I want to remind you of the thing we talked about last time, which is Pascal's triangle. So I know I wrote it on the board last time because we were stuck using the board. But let's go ahead and go to the next page for a second. So here's good little Pascal's triangle. Starts with some ones, and then 1 plus 1 is 2. 1 and 1 plus 2 is 3. 2 plus 1 is 3. And then 1 plus 3 is 4, 6, 4, 1. And you can keep going literally forever. What I want you to see is that these numbers show us or help us expand out x plus h to any power. X plus h to the 0th is 1. X plus h to the 1st is x plus h. X plus h squared is x squared plus 2xh plus h squared. X plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed. The pattern being, these numbers are the coefficients, and the powers of x, you always start with x to whatever the highest power is, and then you just let the power of x get 1 less and the power of h get 1 more. So each term, the powers should add up to whatever your initial power is. So in this one, all the powers add up to 3 in each of the separate terms. In this one, all the powers add up to 2 in each of the separate terms. And if I was going to write an x plus h to the 4th, it would be x to the 4th plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the 4th. And one could go on, but we don't need to go on. But this shows us something. If I want to find the derivative of x cubed, it's going to be the limit as h goes to 0 of x plus h cubed minus x cubed all over h. When we multiply it out, we're going to start to notice something. Well, first of all, the x to a power terms are always going to cancel out, right? That first x to the whatever minus the same x to the whatever, they always cancel. Everything else has an h in it. But you'll notice that the powers of h increase. So the first term here has an h to the first, and everything else has an h to a higher power. Meaning when I factor out an h, the first term won't have any h's left in it, but every other term will. So when I write this, I'm going to get the limit as h goes to 0 of h times 3x squared plus 3xh plus h squared. These h's cancel, and then the rest of the h's get to go to 0. 3x squared plus 0, which is 3x squared. So what ends up being very, very important is this first term is kind of all that matters. What time have I got? I got 5 minutes. Okay, cool. So yeah, we can do this. So what do we think is going to happen with x to the 4th? Well, let's see. F of x equals to x to the 4th. The derivative is going to be the limit of h goes to 0 of x plus h to the 4th minus x to the 4th over h. When we multiply that out, we get x to the 4th plus 4x cubed h plus 6x squared h squared plus 4xh cubed, plus h to the 4th minus x to the 4th. Tight squeeze. All over h, and then the x to the 4th cancel. And what's the only thing that's going to matter? Right, the 4x cubed. Everything else has too much h to count. So this is going to be the limit as h goes to 0. You can skip the factoring. You can just cancel an h from each term. Take the limit h goes to 0 of 4x cubed plus 6x squared h plus 4xh squared plus h cubed. With all of these go to 0. Left the 4x cubed. So what if we had x to any power? I should really say x to any integer power, positive. What if I want to find the derivative of x to the pth power? Well, I'm going to do the limit as h goes, I should write f prime of x. Limit as h goes to 0 of x plus h to the p minus x to the p all over h. So now here's where we need to kind of refer back to Pascal's triangle in a second. When I multiply out x plus h to the p power, what's my first term going to be? X to the p. And my next term is going to be something times x to the p minus 1 times h to the first. Can anyone tell me what that coefficient is going to be there? Let's look. Oh, I think I heard someone say it. It is going to be p. So, right. So if you look at these coefficients, this is from x plus h squared. And this is from being cubed. This is from being to the fourth. It's from being to the fifth. Whatever power you're being raised to, the second term always has that coefficient or that power as the coefficient. Always true, right? Because, right, look, the next one has to be just one more. It's always just one more. It's always just one more. So that second term for any row has the power as the coefficient. Great. So that means I have a p times x to the p minus 1 times h. And we're not going to worry about what the other coefficients are because we know all those terms are going to go away. Right? There is some number. I don't care what it is. Some number times x to the p minus 2 times h squared. Plus a bunch of other terms all the way down to p times x times h to the p minus 1 plus, come on, you can fit, h to the p minus x to the p. I know the last one, or the second to last one, is also a p because there's symmetry in Pascal's triangle. Right? It's 1, p, bunch of other things, and then p, and then 1. That's what we have here. A 1, a p, a bunch of other things, and then a p, and then a 1, and then the x to the p. I thought I saw a hand somewhere, but no. All right, we'll check this out. What we think is going to happen is going to happen. The x to the p's cancel. Every other term has an h in it. So we're going to divide each thing by h. P times x to the p minus 1 times h divided by h is just p times x to the p minus 1. And then everything else has at least one h in it. I've got something times x to the p minus 2 times h to the first. And then a bunch of other terms that all have h's up to the last couple things. P times x to the 8 times p times x times h to the p minus 2, because I divided out an h. So I have 1 less h. It was p minus 1, now it's p minus 2. And then finally h to the p minus 1. Nope, not divided by anything. I did just cancel an h. And then all of these get to go to 0 as h goes to 0. So we're left with p times x to the p minus 1. And that's the power rule. So if your function is x to a power, the derivative is that power times x to the 1 less power. Technically, we have only shown it's true for positive integer numbers like 2, 3, 4, 5, 6, 7, 8, 9, etc. But this rule is true for any power of x. So this is true for any real number p. Meaning, if my function was x to the pi, the derivative would be pi times x to the pi minus 1. Even though pi is not an integer, real positive number. Or if my function was 1 over x to the 7th, my derivative would not be 1 over 7x to the 6th. I would be smart and rewrite this as x to the negative 7. And then I would apply the power rule and say the derivative is negative 7 times x to the negative 8 because it's negative 7 minus 1. So the power rule works for any power of x. Just have to make sure you're writing as x to a power, not like 1 over x to a power or some other thing. So we'll talk more about this, on Wednesday.